The problem is, what's the minimum distance from point P to the line, where point P has the coordinates shown and the line has the shown symmetric equation? What I'd like you to do is pause the video and solve the problem completely to get an answer. As a reference, it took me about 4 minutes to solve this problem. So pause the video. The answer is 4 times the square root of 5 over 5. If you got it, great. Even if you did, you may just want to watch the rest of the video to get some helpful hints and a better understanding of the problem. What I've shown on the right is a general representation of a Cartesian coordinate system with unit vectors I hat, j hat, and k hat. An orange line drawn. Orange line is going through point 0 and point 1, and there's a point P shown. We're going to use parametric equations to solve this problem, and we'll define a parameter t, which is such that it runs along the line, and at t equals 0, it's coincident with point 0, and when t equals 1, we're coincident with point 1. A little bit of thought process on the theory we're going to solve this problem. First of all, as shown like in the orange line, 2 non-coincident points define a line, and 3 non-collinear points define a plane. So we have 3 points, and I'm going to say in this problem that point 0, point 1, and point P are these 3 points. There is a plane, if these points are non-collinear, there's a plane, a singular plane, which contains these 3 points. And I've drawn this kind of as representation of this teal color, a plane, and imagine that all 3 points, point P, point 0, and point 1, lie on this plane. For the shortest path between the point P and the line, we know the answer will also lie on that plane. I define a point Q on that line. The shortest distance will be such that the vector going from point P to point Q will be perpendicular to the line. And another thing we know is that if I have 2 perpendicular vectors, the angle between them is 90 degrees. And we know something about dot products. We know the dot product with 2 vectors, which is a scalar. If I have vector A and a vector B, the dot product is the product of the magnitudes times the cosine of theta, included angle between them. Or it's also on the lower equation is the dot product is the product of the A components of each vector plus the product of Y components plus the product of the Z components. And we know the dot product of 2 normal vectors is 0 because the cosine of 90 degrees is 0. So when vectors are normal, that summation product is equal to 0 as shown. Thinking about the general form of a symmetric equation, as shown right here, it has numerator and has 3 terms that are equal to each other, and each term has a numerator and denominator. In this general symmetric equation form, it's very critical to maintain the order. For example, on all 3 equations, you can in the circles, I have shown the coordinates of point 0. There's a numerator x0 in the term in the farthest left, and the denominator there's the coordinate of point 0, the x coordinate of point 0. In the middle equation, it's the y coordinate of point 0 over the y coordinate of point 0, and the farthest right has the z coordinates. And then in the numerator, the first term is the variable. So for example, the farthest left equation, it's variable x, the middle is variable y, and the farthest right has the variable z. And then in the denominator, under the variable, is the coordinate of the ending point of the line. So that'd be point 1. So we have coordinate x1, coordinate y1, and coordinate z1. And we always, when we have the symmetric form of the equation, this is the way we'd like to do it because we always want to have the coefficient of the variable term to be 1. So it's 1 times x, 1 times y, 1 times z. It's a positive, and maintaining this order will ensure you don't make a simple sign error. Now, a powerful fact of this line is we can consider that there's as you can see in the graph, I've now drawn this magenta vector, point 0, and ending point, point 1. And it's it's on, obviously then it's 4 fourths on the line. And in the symmetric form of the equation, you can see that the denominator is on the farthest left term, it's x1 minus x0. So the x coordinate of 0.1 minus x coordinate of 0.0. And that's typically given the letter A. And in the middle term, the denominator is the y coordinate of the endpoint, 0.1, minus y coordinate of the starting point. And the same thing, the term on the right has the z coordinates. And the A, B, and C variables are typically what are used, and they're called in many texts the direction numbers of the line. Other texts call them the direction ratio of the line. But you can see all that really is it's a vector, as shown in the graph. The vector A, B, C is just the vector starting at 0, going to 0.1. Taking the original form of the symmetric equation, you can see I just substituted and put the denominators as the direction numbers A, B, and C. One of the most powerful things you can do, you can see on the equation, originally there's an x variable, y variable, and z variable. And it's very powerful if you can use a parametric equation and parametric parameter such as t to make all three of the left terms equal to t. So all those three ratios equal to t, a parameter t. So as back on the graph, so when t is 0, I'm at 0.0, and when t is 1, I'm at 0.1. When t is going from 1 to 0, I'm on that line somewhere between 0.1 and 0.0 and 0.1. When t is greater than 1, then I'm farther to the right than 0.1 on that orange line. And when t is less than 0, then I'm to the left of the 0.0 on that orange line as it extends. You can see in the equation we have actually three equations, because we have an equation involving the x coordinates equal to t. And so if I just focus on that one alone, it's x minus x0, the x coordinate of this 0.0 point, over the direction number A equal to t. So that's one of the equations I can get of these three equations. And if I just do the simple algebra, I can multiply both sides by A, which ends up with getting rid of the ratio on the left and having A times t on the right, and then to add x0 to both sides of the equation. So now I end up with the farthest equation on the right, x equals the x coordinate of 0.0 plus the x direction number, which is A, times the parameter t. So it's almost a good starting point. You can think that, so at t equals 0, just looking at the equation, at t equals 0, then A times 0 is 0, so x equals x0. When t equals 1, and A being x0 minus x1 times 1 ends up with x being x1. So that you can see how, as the parameter changes, the x coordinate is changing. And likewise, you can see is in the middle and the right, this exact same thing can be done focusing on the y dimensions and the z dimension. So now we have three scalar parametric equations for that line. And what we can use those three scalar parametric equations for the line is to solve for the vector form of the line, where simply I take the x scalar equation, which gives me the I hat vector direction, x0 plus at, and then I have a j hat term and a k hat term of this vector form of the line. Since we have kind of a theory and understanding of vector form of lines and symmetric form of lines, we're going to put the original equation shown, into the general form of the symmetric equation using the rules we talked about as far as maintaining order. So you can see on the farthest left term, the coefficient of the x term is +1. And that's the desired form of the equation. So therefore, that term is correct. However, if you look at the middle term in the original equation, the numerator is -2 minus y. We would like to put it in the general form of the symmetric equation. We'd like the coefficient of the y term to be a +1. What we can do is as shown in the equation, we have minus 2 minus y over minus 5. I can multiply both the numerator and denominator of that central middle term by minus 1 in both the numerator and denominator. In the farthest right term, you can see it's z over minus 2. So the coefficient of the variable z is plus 1, so that's in the form we'd like. And now keeping the farthest left and farthest right term as they originally were given, and then multiplying both the numerator and the denominator of this middle term by minus 1, you can see now that it's y plus 2 over 5, which is in the general form of the symmetric equation. We know at t equals 0, if you look at the general form in the numerator, for example, it's x, the farthest left term is x minus x0, and in our equation we have x minus 2, so x minus x0, therefore x0 must be 2. In the middle equation, this is y plus 2, and we know it's in the general form it's y minus y0, so therefore y0 must be a minus 2. And the farthest right term would be y minus z0, and therefore z0 must be 1. And we know since the equation is in the standard form where the coefficient of the x, y, and z variables are all 1, then the denominator will be the direction numbers of the line. So a is minus 1, b is 5, and c is minus 2. So now that we know the coordinates of point 0, the x0, y0, z0 terms, and we know the direction numbers, we can substitute those coordinate values and the direction numbers into the vector form of the line. x0 is 2, and the direction number a is minus 1, so it would be minus t. As far as the j hat term, the y0 term is minus 2, so minus 2 plus b times t, and b is 5. And in the k hat term, the z0 is 0, so 0 plus ct, where c is minus 2. So now we have the vector form of the orange line. A vector pq can now be defined, where p was an initial given point, and q is any generic point on the orange line. And we know, like for example, the I hat term of this vector pq, the I hat term of q is 2 minus t, and we subtract from that the I hat term of the x coordinate of p, which was given as 3. And use the same thing for the j hat term. For example, the k hat term, the k hat coordinate of this generic point q is minus 2t, and we subtract from that the initial point, which is the value pz, which was given as minus 2, so it would be minus a minus 2. And then doing the algebra on the I hat, j hat, and k hat terms, we end up with the I hat term of this vector pq, which has the starting point, the given point p, and at any point q along the orange line, the I hat term is minus t minus 1, the j hat term is 5t minus 3, and the k hat term is minus 2t plus 2. The vector shown in pink, which is the vector with starting point 0 and ending point 1, is lying on top of the orange line, and therefore it's parallel to the orange line. And we know that vector can be described as the I hat coordinate is the x coordinate of point 1 minus the x coordinate of point 0, which is defined as a, the direction number, in the I hat direction. In the j hat of vector 0, 1 is b, which is the y coordinate of 1 minus the y coordinate of 0, and the k hat term of this pink vector is the z coordinate of point 1 minus the z coordinate of point 0, which is also defined as c. And for this example, therefore, the I hat term is minus 1, the j hat term is 5, and the k hat term is minus 2. Taking now the dot product of the vector pq dot the vector 0, 1, we add the products of the I hat terms plus the j hat term plus the k hat term product. So for the I hat term, the vector pq has an I hat term of minus t minus 1, and that gets multiplied by the I hat term of vector 0, 1, which is minus 1. But the j hat terms, the j hat term of vector pq is 5t minus 3, and the j hat term of vector 0, 1 is the b direction number, which is 5. And for the k hat terms, the k hat term of vector pq is minus 2t plus 2, and the k hat term of vector 0, 1 is the direction number c, which is minus 2. And so this is the dot product of any of the vectors, the green vector dot the pink vector. But we know that there's a special desire. We want to find that point Q, which those two vectors are perpendicular, and therefore the angle between them would be 90 degrees, and the cosine of 90 degrees would be 0. So therefore, that dot product value will set it equal to 0, and that will be used to find the singular point Q at which the vector PQ will be perpendicular to the vector 0, 1. So now you can see we have an equation that's a function of the parameter t. Solving for t then, we can do the multiplication of minus t minus 1 times minus 1, which gives me t plus 1, and do the same thing for the product of the j hat terms and the product of the k hat terms. Set that equal to 0, and then solve for t. So we have 30t equals 18, or t equals 18 over 30. We can divide both the numerator and denominator by 6 to get t equals 3/5. So now we know q lies on the direction vector 0, 1. It also lies on the orange original line, and it happens to be at the point where t is 3/5. So it's a little bit closer to point 1 than it is to point 0. Finding now the coordinates of this special point Q, we know that point Q lies along the orange line, and all points that lie along the orange line follow the vector form of the line, but they're at a particular t. At this point, we know now t, the parameter t for point Q, the special point, which is the case where the vector PQ is perpendicular to the line, is at t equals 3/5. So taking the vector form of the line, we know the I hat term is 2 minus t. So substitute now for t being 3/5. And then for the j term, it's minus 2 plus 5t. So minus 2 plus 5 times 3/5. And for the k hat term, minus 2 times 3/5. We can solve for now q, the special point q, which with the point where the line and the vector from pq are perpendicular, has a x-coordinate of 7/5, a y-coordinate of 0, and a z-coordinate of minus 6/5. Having now the coordinates of the point Q and the point P, we can solve for the distance from point P to point Q. And it's simply the square root of the sum of the squares of the x difference and the y difference and the z difference of these 2 points. I like to think of this as equivalent to like the Pythagorean rule, because we know that in the Cartesian coordinate frame, the I hat, j hat, and k hat vector directions are perpendicular to each other. Therefore, the distance squared from P to Q is the sum of the square of the differences of each of these components. So putting now to the equation, the distance from PQ, the square root of the x-coordinate of point Q minus the x-coordinate of point P squared, and so on for the difference in the y-coordinate squared plus the difference in the z-coordinate squared. So putting it in there, we simply end up with the distance, which ends up being, there's a 5 squared term in the square root in the denominator, so that's just 5 in the denominator. The numerator is square root of 80, and square root of 80 is the square root of 16 times 5. Square root of 16 is 4, so the final answer is 4 times the square root of 5 over 5.